So in this video we're going to find the cyclotomic polynomial when n is 20, hence the 20th cyclotomic polynomial. Now we write this with capital letter phi, subscript whatever value we want, so in this case we want the 20th, so n is 20, and the variable we use is x. Now today we're going to use the Möbius function. Now in previous videos I've used other techniques which you'll see in the link below. And these cyclotomic polynomials are really helpful when working with roots of unity. So there's a link in the description also as well about those. But let's concentrate now on the formula for cyclotomic polynomials using the Mobius function. Now there's more than one way of finding cyclotomic polynomials, but there is one nice way when you use the Mobius function. Now, capital letter phi, subscript n, and the variable x. And it's calculated by using a product of terms. So the product is denoted by capital letter pi, and then we want the divisors of this n, so we'll come to that in a moment. And then what we do is we have x to the power of that divisor minus 1, so that's the first part of the term, and then we raise it to a power. So we use the mu, which is how we denote we're using the Möbius function, or evaluated the Möbius function, and n divided by d. So that's that value divided by the divisor. So that's the function, the equation that we use. So first of all, let's have a quick run through the Möbius function. So the Möbius function, so mu of n, that takes on three values. Now it takes on the value of 0 if that divisor has a square factor. So has square factor. Now this is the priority when you're trying to find values for the Möbius function at the value n. So for example, if you've got 4, 9 or 16 as a factor of your number, it will take the value 0 and that will be the priority. Now another one we've got is it takes the value of +1 when it has an even number of factors. So even number of factors. Okay, and it takes on the value of -1 when it's got an odd number of factors. So odd number of factors. And there's one rule in that as well, is the Möbius function calculated at 1 is +1. So that's one rule we need to stick by as well. So that's the Möbius function. So now let's move on to the divisors of our value for this polynomial here. Now if we've got n equals 20, our divisors of that, pretty straightforward, elementary maths. We've got 20 times 1, 10 times 2, and 5 times 4. So that's all of our factors. So we've got 21, 10, 2, 5 and 4. They're the numbers of interest for us. So let's work out what we need for the Möbius function here with n divided by these divisors. So our divisors, if I list them, I've got the divisors, I've got 1, 2, 4, 5, 10 and 20. And I'm interested in this value here, n divided by d. So n divided by d. So in each case, n is 20. That's the bit we need to remember. So here I need 20 divided by this 1, so I've got 20. 20 divided by 2 gives me 10. 20 divided by 4 gives 5, gives me 4, gives me 2 and gives me 1. Okay, so now what I need now is the Möbius function of that value, n over d. Let's put that as n over d. So now I've got mu of 20, mu of 10, mu of 5, mu of 4, mu of 2, and mu of 1. So I need to evaluate those values. So mu of 1 we know straight away is 1. That's pretty straightforward. 4 and 20, well, they have factors of or divisors of 4, and this one obviously has got 4 in it as well, so those are squares, so they take on the value 0 automatically. Now if you want to see how these values are done in more detail, there's a link below to show how that is calculated. So I'm just going to run through these pretty quickly today because I want to concentrate on those. Now the value at 2 is -1, as is the value at 5, and 10 is +1. So they're the values of interest that we need for this question today. So with this taken care of, we can now go through this formula here and we can sort of set up how we're going to calculate it. So we need the product of all of those divisors, x to the d minus 1 and this Möbius function value which we've got listed here. So let's go through it. So for n equals 20, let's just write that there. Capital letter phi, 20 of x. So now we need x to the power of the divisor minus 1. So let's start off with 1. So I've got x to the power of 1 minus 1 to the power of 0. That's the n over d. So that's 0. So that's the first one. Now when d is 2, I need to raise to the power of 1. And then I've got x squared. So x to the power of 2 minus 1 raised to 1. Next divisor I've got is 4. So now I've got x to the 4 minus 1. And x to the 4, my value is -1 for my mu of n over d. Now I've got 5. So I've got x to the 5 minus 1, and that's to the power of 0. And then I've got x to the 10 minus 1, and that's raised to the power of -1. And finally x to the 20 minus 1, and that's raised to the value of 1. Okay, now that's all looking all well and good, but it's a little bit scruffy and a little bit disjointed really, and trying to simplify things up. So we know that anything to the power of 0 is always 1. So basically we can cancel these ones and this one out, so they can be taken away. When it's to the power of -1, it goes in our denominator. Power of +1 goes in the numerator. So what we've got here now, we've got 1 times x squared minus 1, that'll be in the numerator. This one will be in the denominator because it's got to the power of -1. So I've got x to the 4 minus 1, so that can stay like that. This is just another 1, so that's another times 1. X to the 10 minus 1, because it's to the power of -1, that will go down to the bottom in the denominator. So x to the 10 minus 1. And this one's +1, so that's x to the 20 minus 1. Okay, so now we can just simplify things off a little bit. Now, what can we do here? Now we can maybe just multiply this all out and do polynomial long division, or we can try and factor things out and see if we can get some calculations, some cross cancellation somewhere. So let's have a look what we can do. X squared minus 1, I'm going to leave that as it is. The ones I can ignore. Now x to the 20 minus 1. Now I could rewrite that as a difference of two squares. So that would then become x to the 10 minus 1, x to the 10 plus 1. Now that becomes really useful because I've got x to the 10 minus 1 in my denominator, and I'm going to be able to cancel that out. So I'm going to rewrite this as this. So now I've got x to the 10 minus 1, x to the 10 plus 1. And I've got x to the 10 minus 1, so I'm going to stick that in there straight away. Now x to the 4 minus 1. Now I know that can also be the difference of two squares. So if I just put a line there, x to the 4 minus 1, that becomes x squared minus 1, x squared plus 1. That's my difference of two squares. So that one there, if I can write -1 squared, that's what I've got. So that's my little scratching work. So I can rewrite that x to the 4 minus 1 as this. And I've got an x squared minus 1 here in my numerator. So good things could happen here. So now I've got x squared minus 1, x squared plus 1. Okay, now I cancel that out, cancel that out, cancel that out. Sorry, wrong one. Cancel that out and cancel that one out. Sorry, keep this one. So I'm going a bit too quick there. Okay, so now I can rewrite things as x to the 10 plus 1 and x squared plus 1. So that's what I've got. Now what about x to the 10 plus 1? Now because I've got this, I can take an x squared plus 1 in here, because this is going to have some imaginary values in here. If I try to solve for x, there'll be 10 solutions. So x to the 10 plus 1, I can rewrite that. So let's give ourselves a bit of space here. X to the 10 plus 1. I know in there I've got an x squared plus 1. So I'm going to go along here. I've got an x squared plus 1. Then if I take that out, doing polynomial long division, I'm going to have alternating x exponents going down in powers of 2, because I've got the squared here. So what I will have is x to the 8 minus x to the 6 plus x to the 4 minus x squared plus 1. Now that would also be similar with x to the power of 14 as well. That would also give me then x12, x10 and blah blah blah, and that'd be alternating in its signs. So that's an interesting result there we can use for the x to the 10 plus 1. So x to the 10 plus 1 I can rewrite as this. So that equals x squared plus 1, x to the 8 minus x to the 6 plus x to the 4 minus x squared plus 1. And then I'm going to divide that by x squared plus 1. And look at that, that's really helpful now, because I've got x squared plus 1 in my denominator, so they can cancel out. So my cyclotomic polynomial is all done. I know what it is. So I can write here now, capital letter phi, subscript 20 with variable x, that equals x to the 8 minus x to the 6 plus x to the 4 minus x squared plus 1. And that is my 20th cyclotomic polynomial. And I'm using the Mobius function, and that's how nice is that. That's really helpful. Rather than trying to factor out some big polynomials, this was a nice little way and I had to do it. Okay.